Hey guys, I'm here to run you through some solutions for topic 5, where we're looking at electric charge and Coulomb's law. So, we have two separated identical conducting spheres with charges. I don't need to read this problem to you, you've already looked at it. So, step 1 for this problem is to find the difference in charge between our two spheres, okay? And if we plug in our values for each sphere, when we're finding the difference in charge, we will find that there is a total difference of 16 microcoulombs. So the magnitude of charge is 16 microcoulombs. Now, remember that this charge is going to be evenly distributed across both spheres at the end of this process. Okay, so if we're going to distribute it across two spheres, it makes sense then to divide that charge into two parts. So we divide it in half and we get 8 microcoulombs. Okay, so you can then imagine if we subtract 8 microcoulombs from 4 microcoulombs, positive 4 microcoulombs, we get negative 4 microcoulombs. And if we add 8 microcoulombs to negative 12 microcoulombs, we get the same value, okay? So negative 4 microcoulombs is going to be the charge distributed onto each sphere. Another way that you could possibly think about it is in terms of units of charge, okay? So here I've set it up, so here we have plus signs equaling 1 microcoulomb. We have negative signs equaling negative 1 microcoulomb. And if we imagine 8 of our units of charge moving on to from Q2 on to Q1, then what's going to happen is over here we will be left in the end with, again, negative 4 microcoulombs, and over here as well, negative 4 microcoulombs. Okay. Remember that only negative charges actually move. Positive charge does not. Okay. Only electrons move, at least outside of an ionic solution. Okay, so the electric permittivity of graphite is 12 times larger than that of a vacuum, etc., etc., etc. What does this mean? Well, basically what it means is that an electric field will propagate in a vacuum more easily than it will through graphite. And so it's not the same as resistance. It's an entirely different property. So make sure you don't think of it in those terms. So we have a force between 2 points, 2-point charges in a vacuum, and it's given as F. And then the two charges are embedded in graphite and the separation is doubled. We're asked to predict the new force between the charges in terms of F. And what I've done here is taken advantage of the fact that force is inversely proportionate to permittivity times radius squared. Okay, so we have two types of permittivity here, and we also have two different radiuses. So what that means is that my proportionality is going to look something like this, where on one side I have the force through a vacuum and the permittivity and the distance squared. And on the other side, I have the force through graphite as well as the permittivity of graphite and the radius in graphite squared. Okay, so from this, then, I can solve for the force through graphite fairly easily. And then I can start plugging in my values. And what I will find is that the force through graphite is going to be about 1/48th of the force through a vacuum. Okay, so it's much, much weaker in graphite than it would be in the vacuum. Okay, for 5.3, finally we have something that is actually a little more straightforward than the previous two. We're just asked to calculate the force on each charge. and it's pretty straightforward. So we have two charges of 2 microcoulombs and 8 microcoulombs, and they're separated by 3 centimeters, which is slightly annoying because that means we have to do a conversion, but it's okay, it's not the end of the world. I then plug my values into the formula for Coulomb's law. There's actually not much reason to calculate this product first. You could have just plugged it directly into this equation, and that would have been fine and maybe even faster. I'm not sure why I did it that way, but anyway, after you plug in all of your values, you will find that you have 160 newtons to 2 significant figures. Okay, so 5.4 is a bit of a deal, and that's why I actually moved it on to its own page. Because when in doubt, you should always draw a diagram. And I did draw a diagram here, as you can see. So positive charge Q is placed on a line joining Q1 and 2, Q1 and Q2. So it's somewhere in between there. And we don't really know how far it is. We are asked to determine the distance from Q1 where this third positive charge experiences 0 net force. Okay, so let's take a look at 5.3 just really quickly. So we have a charge of 2 microcoulombs and 8 microcoulombs. So that tells me right away that this charge, which I've called Q sub 0 here, is going to be closer to the smaller charge than it is to a larger charge. Okay, so it's going to be closer to this guy than it is to this guy. And the reason for that is because it is being repelled from both charges, and so the smaller magnitude charge will give less repulsion than the larger magnitude charge. Okay, so I said it here probably much more concisely. All right, so I've done a little bit of a math trick here just because it kind of simplifies things. You don't necessarily have to do it this way, but it's how I did it. There's always more than one way to handle problems like this. But anyway, I knew that it would be useful to express my charges in terms of each other rather than as these kind of absolute values. So here I've expressed Q2 as 4 times Q1 because 8 divided by Q is, 8 divided by 2 is Q. Okay, so anyway, let's look at the math here. We know that our sum of forces on these two charges is going to be equal to 0. So that gives us this initial equation where we have Q sub 1 times our test charge divided by the distance from Q sub 1 squared. And that is equal then to Q sub 2 times the test charge divided by the distance from Q sub 2 squared. So you can see those values on my diagram. Okay, then I can set up a pretty straightforward ratio, and it's actually quite easy to solve this. And you note that the charge, Q, the test charge, actually just cancels right out. So that goes away, and so that makes our equation really simple and easy to solve. So we solve for one of the distances. It doesn't really matter too much which one, but we should look at the problem. It says from Q1, so it makes sense that we would solve for T sub 1. Okay, and then here is where I use my substitution, and this is really, it's a convenient substitution because it kind of simplifies the math. Again, you could have just plugged it in at this point, and that would be fine too. It doesn't really matter that much. Anyway, what you're going to find is that d sub 1 is equal to 1/2 of d sub squared. After you do all of your math, I did skip the square root of both sides. Sorry about that. I do skip some steps sometimes just to save time. Okay, remember that we're given the total distance d sub 1 plus d sub 2. and that is equal to 3 centimeters. And that is from the previous problem in 5.3. Okay, so I can then plug in my value for d sub 1, the value I've solved for, and you do a little substitution, and you will find that d sub 2 is equal to 0.02 meters, and d sub 1 then is equal to 1 centimeter. Okay. So I wanted to add a little more context, which is why I gave it another page here. It got its own page. Sweet. Okay, so number 6 I think is fairly straightforward. Yeah, nothing too crazy here, so I'm not going to go through it, but if you have any questions, don't hesitate to ask. Note that rather than using a square root sign, I've used, I should just tidy that up a little. There you go. Instead of using a square root sign, I've used 1/2 exponent. It's just kind of a convenient way to simplify some of your math, especially when you're plugging stuff into a calculator. I know I've told you this a number of times. Okay, so this one gets a little bit tricky because we're going to dig into vectors, and I know that students just tend to struggle with them a little bit, and I want to make it as simple as I can, but you really do need to be familiar with topic 1.3 from your books and from the IB syllabus. And if you have any questions about vectors at all, and I'm probably going to go through a vector handout with you as well. Anyway, if you have trouble with vectors, do not hesitate to contact me, because that is going to be a kind of crippling problem on topic 5. All right, so let's take a look here. So first one, in an attempt to observe and determine a value for a small electric force, we've set up this experiment where you have these two charged spheres, okay? First, we're asked to draw a free body diagram, and this is actually, they're not just making you do this for fun. You actually have to do this to solve the next parts of the problem. So let's take a look. First, we have the force of tension, and second, we have the electromagnetic force, and that is pointing horizontally away from the ball. They've set it up here so that conveniently ball A and ball B are, you'll note, in a line horizontally. So that's helpful for us. That would actually be very difficult to set up experimentally. But anyway, we then have force of gravity, F sub g, which is equal to gravitational force. So there's your free body diagram. Should look something like that. All right, so for vector analysis, let's take a look at Newton's first law. First, if velocity equals 0, then the sum of forces is equal to 0. And our three vectors must also add up to 0. Okay, what that means then is that the force of tension is going to be equal to the negative electromagnetic force plus the negative gravitational force. And what that also means is that we need to do some vector addition. Okay, so remember that both of these values were pointed in the opposite direction, and this is what their addition would look like. So if we add the gravitational vector, the negative gravitational vector, F sub g, to F sub e, and just put them together like so, we will get our resultant vector for force of tension. Okay, so we have to do a little bit of trigonometry here, where F of g is going to be equal to F of t times cosine theta. Note that we have a right angle triangle. Remember what I said when I said that was going to be convenient? Well, this is that time. So for our right angle triangle, the force of tension is our hypotenuse. If we consider it in terms of a unit circle, the force of tension there would be equal to the radius of the unit circle. Okay, so what that means then is that the force of gravity is going to be equal to the force of tension times cosine of theta. Okay, and what that further means is that I can solve for force of tension in terms of mass and gravitational acceleration and cosine of theta. We are given the angle is 20 degrees. So we now, if we have the mass in the problem, which we do, we now can solve this problem. Okay. Next, we need to find the electromagnetic force, which I've called F sub E. That is quite a messy E. Perhaps I can clean that up slightly right now. And that is equal to the force of tension times sine of theta. Okay, so when we look at this diagram carefully, you will see that that is the case. We'll talk about that in a second. So my electric force then is equal to force of tension times sine theta. And by doing a little bit of substitution, I will find that my force of electromagnetic force then is equal to the mass times gravity times tangent of theta. Okay, so sine of theta divided by cosine of theta is equal to tangent of theta. Trigonometry time. Okay, so then I can actually solve for my electric force because I know everything that I need to know. I have my mass, I have gravitational acceleration, I know how to use the tangent function in my calculator. Smashing. Okay, so I plug all my values in and I get 4.3 times 10 to the negative 4 newtons. Okay, question. Aren't these backward? Typically, cosine of theta is associated with an x value, not a y value. Similarly, sine of theta is typically associated with a y value, not an x value or a horizontal value. But we're measuring our angle, 20 degrees, against the vertical. And what that means is that our normal trigonometric conventions are inverted. Okay. For part C, we now need to calculate the charge on the spheres. So my force is going to equal Coulomb's constant times the product of the two charges times radius squared. We know that those charges are equal, but we still need to find the radius. However, since we're given the length, it is easy to find the distance between them. Remember, that length there is a hypotenuse. This is a right triangle. Let me just make that explicit here with my little Pythagorean box. There we go. See? Right triangle. Okay, if that's the case, it's a very simple matter to find the radius just by using the sine function. You may recall SOHCAHTOA from previous mathematics lessons. I do not use SOHCAHTOA. I use the unit circle, which I may expand on a little bit later just because it's easier and I don't have to remember mnemonics, which I don't like to do if I don't have to. Okay, if I have the radius, then all I have to do is rearrange this equation, and I've kind of skipped through that. Sorry about that. I do skip math quite a lot sometimes, but basically I need to solve for Q. Okay, so here this is the, let me just get rid of that. It's probably not helpful. All right, so I algebraically rearrange this and I get square root of force times the distance squared divided by Coulomb's constant, and that is going to equal my charge. And when I then plug in my values, I will get 5.4 times 10 to the negative 8 coulombs. If you would like me to expand the algebra here, just give me a shout. I'm happy to go through it with you. Not a problem. Okay, so that is A, B, and C for question number 7. A bit of a challenge. Certainly a little bit time consuming, but this should all be review in theory. We're just applying some new ideas, okay? But the algebra you should be familiar with, the trigonometry you should be familiar with. Vector addition is certainly going to be a review. And as I said, I may go through this in more detail at a later time, just to go through vector addition with you guys. But anyway, that's my lecture, that's my handout. Hopefully, I don't expect you would have answered all these questions probably without a little help. But hopefully it all is making sense at this point. Try it yourself now that you've seen the solution. Work through it on your own. Refer to this as needed and let me know if you need assistance. Have a great day.